We are good to go. Can anyone please let me know whether my screen is visible or not?
Yes,
Yes,
sir, it's
sir, it's
visible.
visible. Okay, great. So I guess we are good to go. Let me just hide this. Let me just turn on the laser pointer. Yeah, so we are good to go. So welcome all of you again for the first live problem solving session for this course, Analog IC Design, which is being conducted by Professor Sankaran Aniruddhan. I have just given my introduction. So this will be the session organization. We will have first 60 minutes of session, then we will take a 5 minutes of break, and then again we will have the remaining session of 50 or 55 minutes depending on how much content is still remaining. And one more thing, I guess NPTEL will be having some delay in uploading in sharing the Excel sheet, where I will be sharing the link towards the YouTube channel as well as the folder. So this is the YouTube channel where I will be uploading the recording of this lecture, and in the description section of this of that recording that is uploaded on the YouTube, that will be uploaded on the YouTube. So you'll be able to find the notes, the slides that I am presenting right now. So if I forget, then just let me know to copy paste this link into the chat section during the break time. Someone just please remind me, okay? And so the way the today's session will be conducted is, see, I just want to give you a very good feel of this subject as to why you want to study the subject. We may not be able to solve a lot of numericals today, so just hold on there. Like from the next session onwards, we will solve a hell lot of numericals. But for today's lecture, it is very important to give you the complete feel of the semiconductor industry and where the analog IC designs market currently stands out, right? So almost 80 to 90% of the presentation that I'm gonna do today, it will be based on to give you the entire feel of the market as well as the jobs as well as what is actually going on in the industry. And in the remaining time, we may be able to solve 2 or 3 numericals which may help you to solve the assignment questions that are there on the based on the week one's content. Correct? So now let's have a overview of the semiconductor industry, but before that, take a example and let's understand what is happening over there. So let's say this is the image that you have taken on your phone, and now from your phone you want to send out this image wirelessly over the wireless link to your friend's phone, right? So first of all, this image is nothing but this is a what you can say RGB image, right? You may study in the digital image processing course. If you take it in your third or fourth year, it will be converted into the bits. Now those bits, we need to convert them into the analog form again from the due to the based on the digital to analog converter. And now all this information will be put on top of a carrier. This carrier will ensure that your signal will be able to you will be able to transmit your signal wirelessly, correct? So now this carrier will be generated by a block called as a phase locked loop, and this modulation that happens, right, this block is called as the modulator or IQ modulator, or you can also call this as a mixer, correct? And now once you have this signal, let's say this may be a LTE signal which may be around 900 megahertz, and this is the information that you want to wirelessly transmit. Now once you have this modulation present, now you know that you may be far away from the destination of your friend, or you may be standing far away from the base station, maybe Geo, maybe Vodafone, maybe Airtel, correct? Now you want to ensure that you are pumping out a sufficient amount of power from your mobile so that that signal actually reaches the base station, and base station will be able to decode that signal. Will be able to decode means there will be a sufficient signal to noise ratio that will be available at the base station, so that base station can receive this information, correct? Now this is one part. Now from that base station, let's say your friend stays nearby only, let's say 1 or 2 kilometers away from you. Now the same base station will now transmit that signal whatever you have transmitted to your friend's phone, correct? Now at that particular now in this particular chain, the reverse of the flow that I have just told you, it will happen. First the signal will hit on to the antenna of your mobile, then it will go through a block called as the low noise amplifier. This is called as LNA, correct? Now what does this low noise amplifier means? You know that each and every amplifier will add its own noise, correct? So if you take a amplifier, let's say you have a signal at the input, noise at the input, and at the output of the amplifier you have signal and the noise. So amplifier, even though it amplifies the signal, but it degrades the SNR compared to input. For example, if you have a 15 dB of SNR at the input of the amplifier, then at the output of the amplifier you may be losing around 0.5 or even 1 dB of SNR. Correct? So each and every amplifier will add its own noise and degrade the SNR. Now how can I design an amplifier which will add as little noise as possible and also amplify it at the same time? Correct? So that job is going to be done by this low noise amplifier. And what is this diplexer and all? See, you know, this is a complicated circuitry. You have to transmit not only on 4G, but if the 4G band or something, your connectivity is not available, your phone should be able to transmit on the backwards generation, that is 3G or 2G as well. Correct? So these diplexers are nothing but it will combine the signal from multiple bands and it allows those signal to share the same antenna over here. Of course, it assumes that the antenna will be having a bandwidth which can transmit all those bands over there. Correct? And once you receive those signal, you again do the down conversion operation using the mixer over here. You use the same phase lock loop, you use the phase lock loop that you had used on the transmitter, and then when the signal is down converted, you try to amplify it, filter it out. Correct? And then the signal is ready for the digitization, that is going to A to D converter. And once you have converted the signal into the bits, you try to reconstruct the image. So this is the entire flow that is happening. Now, why did I tell you this flow? I just wanted you to visualize how many blocks are going on in this particular simple operation. This part that you're seeing over here, also this part, the mixers, the power amplifier, low noise amplifier, this part will be taught in the RFIC course, not in this particular course, because this is a high frequency circuit design. The focus of this course will be only on this particular part. Whatever will be present after the down conversion, that will be the focus of this particular part. That will be the focus of this particular course. Okay, I hope till this point it is very much clear. Now, who decides how much SNR will be required to decode this signal properly? If you have studied the digital communications, then there are some diagrams which we call as a constellation diagrams, right? And the more complex this diagram is, so this x-axis is nothing but your I, and the y-axis is nothing but q. So this is what is called as a IQ plane. Now, the more the dots that are present in this IQ diagram, right? Now there is a good chance that this dot can move from here to here because of the noise. Correct? Now, when this diagram, just imagine that this diagram is given to the receiver, and receiver will try to interpret whether this bit which is transmitted, whether this is actually representing this bit or some adjacent bits that are present over here. Correct? If the noise is higher, this bit can actually shift to right, left, downwards, anywhere. Correct? Now, the more complex this diagram is, higher the signal to noise ratio required to exactly decode this bit. Correct? Not bit exactly. This is we called as a particular point in the constellation diagram. So if you transmit this particular sample, you may be actually transmitting 4, 5 or 6 bit depending on the complexity of the constellation diagram. Correct? So now this is what has been shown. This is a typical favorite curve of digital communication engineers, the SNR versus BER curves, and this is exactly showing you this. So from the QPSK to 1024 QOM, the complexity of this constellation diagram actually increases, and you are trying to fit more number of dots in the same amount of area. Correct? So now if you look at let's say 10 SNR, correct, if I just have a 10 dB of SNR, correct, then the probability, the bit error rate is just 10 to the power minus 5. What does this mean? Out of 10 to the power 5 bits that I transmit, only 1 bit will be having an error. But just look at 1024 QOM, correct? The bit error rate is very close to 1. So what does this mean? If I transmit 2 bit, 1 bit might be corrupted out of it. Correct? So that is not a good thing. So this is how the SNR is actually decided. Now coming to the main part, what does analog and RF engineers actually do in their job? So now I just categorized it into two main categories. One is analog and mixed signal design engineer, even that is subcategorized into analog and mixed signal, and other is called as a RFIC design engineer. Now coming to the analog design, so you will be basically designing the op-amps. Op-amps for what? Maybe you want to design a very high speed comparator. Maybe you want the op-amp to be that will be going into the ADC. So according to the different applications, the specs of the op-amp will be changed, and the main focus of this course will be to dissect this op-amp, study the different topology, and at the end of the course you should be able to select the topology of the op-amp and for that particular application. So not only you should know the design of the op-amp, but which topology of op-amp you should select for a given particular application. Now there are some circuits called as the band gap reference circuits. So they provide you a very accurate reference voltage. These are basically used in the, what you can say, the voltage regulators are there, like the low dropout regulators and all. So this band gap reference circuit is actually used over there. Now the third area is about the power management integrated circuits. I will go through it. I have a dedicated slide for this. Now the next one is the high speed analog design, that is the wireline communication. Now you know that when you have a if you have a chip, then there is a processor, there is a memory, there is a very fast communication that needs to happen between the processor and the memory, so that there will not be any delay between that processor. When when the processor has to perform something, it has to take the data from the memory, again has to store back the data into the memory itself. So it has to do this operation every cycle, right? And if I face a delay between the interface of the processor and the memory, then the speed of the operation is going to be less. You cannot ramp up the speed of your processor, because there is a choke point that has been created over there. Correct. I also have a slide on this. Correct. And the next one is design of the active and the passive filters. In the application case study, you will be able to see all this. I have around 2 or 3 application case studies with me. The next one is the mixed signal design. So these guys basically design the analog to digital and digital to analog converters that I had shown in this particular diagram. This D to A and A to D converters that you are seeing over here. So this job is actually done by the mixed signal design engineers. And the RFIC design engineer, I won't go a lot detail into it. So whatever blocks I told you that are present over here, including the low noise amplifier, power amplifier, as well as the modulators and the demodulators that are present over there. So those designs will be handled by the RFIC design engineer. Correct. Now this is what I was talking about, the wireline communication. So if you look inside a data center, right? So if you want to watch any movie on the Netflix, so all of that content is actually hosted in the data center, correct? So now if you visit the data center, you will see there are multiple racks that are present, and inside one of the racks, if you see one of the rows, you will see many PCBs like this, correct? So the communication that happens between the CPU that you are seeing over here, the processor, as well as the memory, or the two different chips that are placed on the PCB. So this is what we call as a wireline communication. Why wireline? Because there exists a physical medium to transmit the signal from the CPU to the memory. So that line actually exists over there, correct? That is why it is not called as a wireless, it is called as a wireline communication. And these speeds are typically way too higher compared to the wireless communication. Just to give you an example, if you are targeting around, let's say if you are getting around 50 or 100 Mbps speed from your Wi-Fi at your home, these speeds will be typically around 15, 20 or even sometimes up to 30 or 40 Gbps, correct? So this is how crazy the communication goes on between the CPU and the memory. Now this is just a block diagram that I just wanted to show you that the physical channel actually exists. And if you have studied the electromagnetic theory, if you have a signal which is having such a high frequency content, then this channel does not remain as a normal line. You have to treat it as a transmission line, correct? So this is the only thing that I wanted to show you, not going into too much technical details right now. Coming to the power management side, so this is the typical power management system that is present in your mobile. So now you at least need around 20 or 30 different supplies for different things that are there on your mobile. So this is a CPU, right? It will be designed in the state of the art technology node, that is maybe 3 nanometer or 5 nanometer TSMC technology, right? These RF front ends, they will not be designed at that particular state of the art technology. I will give you the reason for that maybe in next few slides. Okay, the display needs certain voltage, your motor is there, the cameras, the audio codecs, the audio amplifiers, all of them will need different voltage. So it is a job of this power management system to ensure that all these voltages are available from a single battery voltage, correct? And you will see that when you try to study everything, you will see that 80 to 90% of all the voltage conversion, that is from this battery voltage to a particular voltage that is required for that particular what you can say particular thing, maybe the motor or the LCD display. So that conversion, 80 to 90% of those conversions happen using the switching regulators, and the rest of the conversions happen using the LDO regulators. So if you study the power management course after taking this analog IC design, you will be able to easily know the reason for that. Right. Now coming to the breaking down, let's say this is the best possible breakdown that I was able to get on the internet. So this may be a little bit old, but for very latest phone, I did not find a very clear picture like this. Okay, so bear with me for that particular thing. Now, if you try to see what all blocks are present inside this iPhone 7 chipset, right? So you have your audio amplifier, you have the RF transceiver that is present over here. So just to give you some example, the RF transceivers, you will see Broadcom and the Qualcomm, they are very much they are very specialized in this particular domain. So you will see a lot of chips from Broadcom and Qualcomm, which having the RF transceiver, maybe for Bluetooth, maybe for Wi-Fi, maybe for cellular transceivers, right? So you have the power management chip that is present over here, and these small things that you're seeing over here, small white or whitish yellow patches that you're seeing over here. So these are all the passive components, that is the capacitors, the resistors that you were not able to put on the chip. Why you were not able to put it on the chip? Because they occupy a lot of area. You don't want to pay a foundry such a high cost just to fabricate the passives, right? So that's why you have many passives that are present around the chip, and this would have taken a lot of area. That's why they have been taken off the chip. So just to give you an example, you may be able to easily put some picofarad, even 10, 15, 20 picofarads of capacitor on the chip. But if you require a microfarad of capacitor, right? Pico is 10 to the power minus 12. Micro is around 10 to the power minus 6, right? If you want to put a microfarad of capacitor, it is impossible to put it on the chip because it will occupy the entire area of the chip itself, correct? So now I hope you are able to see at least some of the blocks that are present. The image that I had shown you, where we wanted to transmit some image from the phone to another phone, right? So at least you are able to see some of the blocks, the RF as well as the analog blocks that we had talked about, along with the power management blocks. Correct. Now let's go through the overview of the semiconductor industry. By the way, guys, I won't be able to see any questions if you type it on the chat section. Please feel free to poke me at any point if you guys have any doubts. Okay. Now let's look at the size of the semiconductor industry. Correct. So now this report has been taken from the McKinsey and Company, favorite company for MBA guys. Now, as of 2021, the size is close to $590 billion, and it is expected that by 2030 it will reach around $1 trillion. Just to give you a comparison, currently the IT industry market size is close to 1.2 to 1.3 trillion dollars. Correct. So now the semiconductors are expected to reach there by 2030. Now, out of this $590 billion, the only 60 to 65 billion dollar of market it belongs to analog ICs, and around 20 to 23 billion dollars market belongs to RFIC. So at least from this diagram, it is very much clear that market is not driven by the analog as well as the RFIC guys, right? The market is completely driven by the digital guys. So digital guys will dictate the need for what they want exactly. The foundry will work accordingly. That is why we have been constantly pushing the channel length of the devices that we have been fabricating all down from maybe around there at one point of time there used to exist the devices which were having the channel lengths of around 10 micrometer. Now currently the latest is around 3 nanometer. So that is the amount of scaling that we have been able to achieve. So now one question that will arise in your mind, does this scaling actually help analog and RFIC guys? Answer is depends. At one point of time it used to help a lot, but after that it just started to degrade the performance, right? So I have some slides, we will discuss on that, correct? So now let's try to connect the big picture, correct? So now what is this? This is what we call as your semiconductor foundry, maybe TSMC or UMC, correct? So now what they will do, they will fabricate the silicon dies, correct, according to whatever circuits maybe some company has given to them for the fabrication, correct? They will fabricate the silicon dies. Now these silicon dies will be packaged. So in this particular diagram, the gray color thing that you're seeing over here, this is actually your silicon chip, and this black color thing that you're seeing, this is actually a package, correct? And these are what we call as the leads of this package, and these leads is where the contact is made on the PCB, correct? So I hope till this point it is very much clear. Now what is your role over here, correct? So first let's of all understand what this PDK engineer does. See, it's different thing that I'm designing the circuits on the simulator, but somebody has to ensure that if I fabricate a transistor, right, let's say I do a very simple circuit, the common source amplifier, and I got some results on the simulator, maybe cadence, correct? I got a very good gain around 15 or 20 dB, something like that. I got the unity gain bandwidth, whatever I wanted. Now somebody has to ensure that when I fabricate that transistor, it will meet that performance. Its IV characteristics will not deviate a lot from what the simulator is predicting, correct? So there exists one role which actually contacts with this semiconductor device and modeling guys. It also gets in touch with the foundry, and now he makes the model which goes into your CAD tools, that is the synopsis and the cadence, and these models you use while designing the circuit. So you are here, correct? You are the circuit designer. So now you are been using the tools that have been given by the this synopsis as well as the cadence. Now you have something called as a PDK for that particular technology node. So right now at ISC we fabricate the circuits at 65 nanometer as well as 180 nanometer technology nodes from the UMC, not TSMC, because of course we are academic group. TSMC is little bit costly, correct? So now that PDK, the 65 nanometer UMC, right? So now that PDK I have to get it from somewhere, right? So now from where do I get it? So there is I have a slide. Let me go through as per the presentation. I have a slide on that. So you get that PDK and you start designing the circuits. You fabricate, and most probably you will get a very close results to what you have actually got in the simulation. So that is the job of the PDK engineer, correct? And now once you design the circuit, then you do the layout, then you send it for the fabrication to the foundry. Foundry will fabricate the silicon dies, then you have to also do the packaging of those dies, and once you get the package back, then you design the PCB to test this particular IC, and then you publish the result, or you design the product and you just start selling it, correct? So now inside this PDK, what it contains, this is where I was calling these are the technology files, right? These are very specific from foundry to foundry, and from one particular technology node to another particular technology node of one foundry, correct? So now inside the technology files, if you look, you have to capture all the parasitics that are present around the MOSFET, right? You also have to capture the DRC. What is this design rule definition? So I will just take one example of the DRC so that you should not get confused about what this design rule check is actually, correct? So now this is what you generally draw a layout in the cadence, right? So let's say you have a circuit like this. Don't get scared. This is a circuit of the op amp. This is a telescopic op amp. So you will be studying this in the course, correct? Now I just wanted to show you that there is a connection that is going from this particular stage to this particular stage over here. So that the drain of one MOSFET is connected to the gate of another MOSFET, correct? And when you do the schematic, you of course have to do the layout, because you just cannot send the schematics to the foundry. It needs this layout diagram, right? So now after doing the layout, you also send the GDS file, and from that file the foundry actually fabricates your circuit, correct? So now these green color lines that you are seeing over here, so let's say these represent particular metal layer, correct? So this represent a particular metal layer. Now one design rule check example is how close these two similar metal layers can get close to each other, and still after fabrication I will not be shorting these different metal layer lines. I will repeat again, these are two different connections. I don't want them to get short with each other. How close can these two metal lines get with respect to each other? And still my fabrication will ensure that these will not be shorted, correct? Now these metal lines, now if you try to look in the 3D stack, correct? Now this is what we call as the front end of the line. This is where your transistor sits. This is what we call as a back end of the line. What is this back end of the line? Back end of the line is nothing but the metal stack that you use to connect the different transistors that are present in your schematic, correct? So what you can see over here, there are 5 metal layers that have been given to me from that particular technology node, from that particular foundry, correct? And if I want to make a connection from the gate to the drain of another transistor, right, I have to go up from the gate over here. From the poly, maybe I may have to go through the VR to metal 1. Again I may have to go to the up to metal 3, and again from the metal 3 I may have to come down to metal 2, again metal 1, and again maybe I will be connecting somewhere over here. Correct? So this is a long connection that actually happens like this, and these lines that you're seeing over here, these are represented like this in when you design the layout in the cadence. Correct? So I hope the example for this DRC is clear. If you look from this particular stack, I just don't want the CU2 line, just look at my laser pointer, this CU2 line to get short with this particular CU2 line that is present over here. The CU represents the copper. Okay, if these two get shorted, then it's gone completely, because a short has been created and the circuit will not function at all, or its functionality will be completely degraded. Correct? So how close can these two get, and still my foundry will ensure that the fabrication is happening properly. Correct? I hope the DRC is clear. Now if you look at this particular website, Euro Practice IC Services, these will be the different PDKs that they will be giving you. I've just taken two examples. One, the PDKs available from the TSMC, and another is the PDKs that are available from the UMC foundry. Right? Now, what you can see over here is that they have the technology node all the way from 130 nanometer to all the way up to, maybe you can call it as a state of the art 7 nanometer FinFET. Correct? So now one question arises is, why, if the 7 nanometer node is there, why do I need to care so much about this 65 nanometer and 130 nanometer technology nodes? Who is giving the business to this foundry, and who is that old grandpa who is still designing the circuits at 65 nanometer and 130 nanometer? Correct? So this is the question that we have to answer now. So now, to answer that question, first question that we must ask ourselves is channel scaling. Channel scaling means reducing the length of the channel length of the MOSFET all the way from maybe 180 nanometer to all the way up to 3 or 5 nanometer, which is state of the art. Correct? So is this channel scaling which is helping the digital guys to make their processors faster, to make their functionality faster, and to put more transistors in the same amount of area? Is the same channel scaling gonna help analog and RF engineers? Right? So once this question is clear, then we can answer why these so many PDKs are still available. Right? So now let's first have this common source amplifier. By the way, guys, I'm assuming that you will be at least little bit familiar with the common source amplifier, or at least common emitter amplifier, because this course assumes that you have a very little bit understanding, at least a little bit understanding about the analog circuits. Correct? Now, can someone please tell me what is the absolute maximum voltage that this particular node Vout can reach in this circuit?
I mean, it should be such that the transistor still stays in saturation, right?
Yeah, correct. Let's say any particular voltage, even if it is off, I don't have any problem. What is the maximum VDD, right? So the maximum voltage that this particular node can reach is VDD. Now you know that when you scale your device, there is something called as the constant field scaling, right? So you try to shrink all the horizontal as well as the vertical dimensions. So, and you need to make sure that when you are reducing the MOSFET size, right, the electric field inside that devices, it will not cause a breakdown. The fields should not be so strong that it will just cause the breakdown in the device. Correct? So you also have to maintain the field. That is why even when you're let's say reducing the channel length, let's say from maybe 10 micrometer to 180 nanometer, right? You have to ensure that even though your channel length has scaled, your electric field does not increase there. Electric field has to remain constant, right? So now once that part is particularly clear, now let's see what happens. So for 118 nanometer technology node, your particular supply voltage will be close to 1.8 volt, and if you try to go to maybe 28 or even 45 nanometer, this supply voltage from 1.8 volt it will actually drop off to around 0.9 volt or maybe 1.2 volt. Correct? Now can someone tell me what will happen to the output swing of the amplifier if the value of the VDD has been reduced now? What happens to the swing now?
The swing limits will decrease.
Exactly, the swing limit will decrease, right? So very good. So now we face the first issue of the channel scaling with respect to the analog designer guys, right? The swing limits that I was getting in the older technology nodes, I'm not gonna get the same swing limits if I try to design the same circuit in the state of the art, maybe 5 nanometer TSMC technology node. Correct? I hope that part is very much clear. Now coming to the second part, let's take a very simple circuit. if you guys are not familiar with this, then I will highly suggest please revise your analog circuits notes. So this circuit is called as a current mirror, correct? You take a constant reference current source, you dump that current in a diode connected device so that it generates a voltage, and now you give the voltage to the another transistor. So now what happens if the two transistors are sized in the same manner? You should get the same current from this particular transistor over here, correct? Now as you reduce your technology node, correct, let's say from this 10 micrometer to 180 nanometer, now there is one effect called as channel length modulation that I am sure that each and every one of you must be knowing it, correct? Now what does the channel length modulation means? So what is the MOSFET actually, correct? MOSFET is nothing but it should behave ideally as a voltage controlled current source, correct? I hope everybody knows this. So whatever voltage that I will be giving between the gate and the source, it should control the current that is flowing through the drain terminal over there, correct? Now the ideal current source is nothing but whose output impedance is infinity, correct? Output impedance is infinity, meaning that the voltage between the drain and the source node of this MOSFET should not have any effect on the current that is flowing over there, correct? So this is what is represented over here. So if you look at the VDS after the MOSFET has reached the saturation, correct, if I change the VDS from 1.2 to 1.6, you are not able to observe sufficient change in the current, right? So that means dou ID by dou VDS, this is what we define as a output impedance, correct? How much change is there in the current if I change my VDS by a particular value, correct? Oh, in this particular diagram, this has been shown to be very close to 0, correct? So that means the output impedance is infinity over there. If you look at the short channel MOSFET, what you can see over here, if I change my VDS from 1.2 to 1.6, you can see a observable change in the current over here, correct? So what does this mean? The current flowing between the two terminals is now dependent on the voltage that I am applying between the same two terminals. So if you look at the drain and source over here, right, if I change the voltage between these two terminals, the current between the two terminal changes, right? And this is a very basic property of a resistor. So you can think of it as even though I had a very close to infinite output impedance for a long channel MOSFET, for a short channel MOSFET there is some finite output impedance that is present over there, correct? Now this degradation, like how much change in the ID will be there after applying certain change in the VDS, this actually degrades if you move from 10 micrometer to 180 nanometer and from 180 nanometer to 7 nanometer FinFET or MOSFET technology, correct? Now what does this mean? So your output impedance has now reduced from infinity to some finite value over there, correct? Now what will be the cause of this? What will be the trouble for this? So if you just take this particular amplifier, if this is a
excuse me, sir.
Correct?
Sir, you can you just go back to the previous slide once? I have a small doubt.
Sure.
Yeah. So in the channel length modulation, it's usually modeled as a resistor between the drain and source, right? When we are analyzing a circuit or something.
Correct.
Yeah. So that the value of that is 1 by lambda ID, right? Where ID is the quiescent current going through the transistor.
Correct. Yeah.
Yeah. So. Which means that as the lambda so the quiescent current obviously depends on the biasing. So
yes.
So the lambda is a parameter that describes the or that is associated with the short channel transistors, right?
Correct. Yeah.
So as lambda ID, for R1 to decrease, means ideal current source should be infinity. So with not ideal, that means should decrease. It means that lambda ID, as lambda ID increases, R1 should decrease, right?
Yes,
so does that mean that as you decrease the so you're saying that basically as the channel length, when you go on using more and more short channel devices, our channel, the lambda will increase, because of which we are going to have to do this non-idealities such as
you got it. That's absolutely correct. Yeah. Correct.
Okay, thank you, sir.
Yeah, great. Yeah, that was a good point. Yeah, thanks. So now on the similar lines, what sir told. So if your R0 now starts to decrease, right? So assuming that previously R0 was infinity, and even this is a very ideal current source, so R0 was infinity for this particular circuit. So if you connect any load over there, right, so ideally there is no resistance that is present. Now when you start using the short channel devices, the R0 actually decreases now, and your gain is actually limited by GM into R0, correct? So this GM into R0 is what we call as the intrinsic gain of this device, correct? So adding one more point to what sir said, right? So if you look at an older technology node, maybe 10 micrometer, there will be one intrinsic gain for that particular device. And if you look at a current technology node, maybe 7 nanometer technology node, there will be one intrinsic gain available for that particular device. So the value of the intrinsic gain that is available for that particular MOSFET, it will actually decrease when you move from 180 nanometer to state of the art 5 nanometer technology node, correct? So I hope that point is clear. Please feel free to ask any doubts. Okay. So now coming to main point, the sub question that we had asked is whether the channel scaling helps the analog designers or not. So from the 2 points that we have seen over here, it seems that actually when you move to the very state of the art technology nodes, it is not a good idea to design your analog circuits over there, because the available gain, the self gain of this device itself is gonna be low, correct? Now, so what is the problem because of this? So now if you want to get a particular gain, you have to use more and more and more stages, correct, to get the same amount of gain, and that will burn a lot of power, right? So now this is the same thing that I have highlighted over here. 7 nanometer FinFET may give you the best performance for designing the GPU or neural processing units that are required basically to train your neural networks and for inferences, correct? When you are using that particular kind of application, correct? But if you try to design your analog or RF circuits over here, you are just gonna screw up. Now coming to the case of the power amplifier, I will just highlight, since we have taken this common source amplifier example, since the swing limits have reduced now, correct? Since the swing limits have reduced, and what we want from the power amplifier, it has to deliver as high swing as possible to the antenna, correct? Now if my swing limit itself has gone down, how can I deliver a large amount of power? And one more thing that you should note down is that as you move from 180 nanometer, that is older technology nodes, to a state of the art technology nodes, the breakdown voltage of the device actually reduces. So what does it has to do with the power amplifier? The power amplifier, I will just tell you, the power amplifier that is present in your mobile, right? So it may transmit around plus 30 dBm of power. 30 dBm of power is nothing but 1 watt of power, correct? So that 1 watt of power the power amplifier has to transmit, and that correspondingly, see, power is nothing but you can have V into I or V square by R, correct? So particular swing available across a particular load resistor, so that will give you that power. Now to get that 1 watt of power, just imagine the kind of voltage swing that you will be requiring. You may require around 5 or even 10 volt of peak to peak swing across a 50 ohm load to produce that 1 watt of power, correct? Now can your 7 nanometer FinFET device handle those 5 volt or 10 volt? It's very difficult. The probability is that they are just gonna break down if you have a 5 volt or 10 volt of peak to peak swing across a FinFET or 7 or maybe around 14 nanometer FinFET or MOSFET technology, correct? So that is one point. And one more thing is, yeah, I guess this part is okay. I don't want to go too much into RF design, right? So one more thing, we should not forget that the market is completely driven by the digital guys. According to their needs, the market will evolve. We have to adjust in that market and make sure that our components actually work over there, correct? So now there is one more thing. This reduced VDD has been done, the optimization for digital hertz, analog and RF people. And one more thing, we have said the bad things about the channel scaling. There is one more good thing about the channel scaling that actually helps RF designers a lot, not analog designers that very much, correct? It is, but that is called as a concept of FT and Fmax. I will just briefly introduce them to you, correct? So now what is this FT and Fmax? So FT you can consider as the frequency where the current gain of the MOSFET will drop to 1. So now you should first ask me the question, what do you mean by the current gain of the MOSFET? We have studied that the gate of the MOSFET has an infinite impedance, correct? How can the current go over there? You are forgetting that there are parasitics that are present around the MOSFET. So as you go to higher and higher frequency, the impedance of the capacitor goes down, correct? And those capacitors will now start to play a very important role in analyzing the circuits at the high frequency, correct? So when you apply certain current into the MOSFET, even though it seems that the gate has an infinite impedance, now those CGS and CGD capacitance will lower down that impedance, and you can actually formulate a figure of merit called as a current gain, where FT, that is the unity current gain frequency, where the current gain of that MOSFET will drop to a value of 1, correct? And now there is also one thing called as the Fmax. Now what is this Fmax? So Fmax is nothing but the frequency where the MOSFET's power gain will drop to a value of 1. So now if you operate beyond this particular frequency, the MOSFET will not give you any gain, it will actually start to attenuate, correct? So these are the two important figure of merits, and why do they matter so much? So now coming to our analog design part, we are very much interested in this FT. Why are we so much interested? Because as your FT moves higher, right, the higher the value of unity gain bandwidth that you can get from the op amp. So if you have watched week 1's lecture, sir has talked about the unity gain bandwidth frequency of the op amp, correct? So now if your FT is higher, correct, then the UGBW, that is the unity gain bandwidth of the op amp, can also be moved to higher. So if you move from, let's say, 10 micrometer technology node to 180 nanometer technology node, since the speed of your device has increased now, you will be able to get a higher unity gain bandwidth from the op amp which is designed in 180 nanometer technology node, compared to the op amp which is designed around 10 micrometer technology node, correct? And why does this matter? Because if you have a higher gain bandwidth product, correct, then what I can do, I can have a very high 3 dB bandwidth for my amplifier. And why does the 3 dB bandwidth of the amplifier matter? Because if I have a signal coming in the baseband which is having a maybe bandwidth of 50 or even hundreds of megahertz, right, I want to ensure that the bandwidth, the 3 dB bandwidth of my op amp is at least higher than that particular frequency, so that I don't distort that signal. So this particular point I will again explain towards the end of the slides, okay? Just feel free to ask if you guys have any doubts. So with this FT is particularly clear. For Fmax, now why does the Fmax matter? So now the basic thumb of rule is, if you want to design a circuit comfortably, right, a very conservative estimate will be, you can easily design your circuit at FT by 10 or at FT by 8 value. So your FT, let's say, is around 400 gigahertz. You can easily design your circuits maybe around 40 gigahertz. It won't cause a lot of problem, correct? Now why does the Fmax matter so much to RF designers? Because RF designers, let's say you're talking about a radar technology, the radar always needs a very high bandwidth if it wants to if it is being used for what you can say, imaging applications or perception analysis. Perception analysis means it actually wants to map the environment that is present around the radar. So now the higher bandwidth you cannot get at a very low frequency. So if I tell you to design an amplifier which can give me a bandwidth of 2 gigahertz at a center frequency of 3 gigahertz, it's extremely difficult, very very difficult. But if you tell me to get the same 2 gigahertz of bandwidth at around 30 or 28 gigahertz, it is easily possible, correct? So higher the bandwidth you want, higher the center frequency you choose, because this is the concept of the fractional bandwidth, correct, that you may study or you may already be knowing. So you cannot get a very arbitrarily high number for a fractional bandwidth. Usually it is limited to 10 to 20% of the center frequency, correct? So that is why higher the Fmax value is, higher will be the center frequency where my radar can operate, and higher the center frequency, more the bandwidth I will be able to get from the radar. More the bandwidth that I am able to get from the radar, very high quality images I will be able to generate from my imaging radar. Images means not like a camera, it is like these are different images. I will show you, I have those images in the slide, okay? So I hope this is clear. We have already seen this, the back end of the line in metal stack, and this is how the if you take a snapshot, right, if you take a snapshot and under maybe microscope, this is how it will exactly look like, right? Not a low quality microscope, you need a very good quality microscope, and they cost a lot if you want to take an image like this, okay? So now this is how it looks over here, but when you design it in the cadence, right, so this is how it will look in the layout. So these lines that you're seeing over here, the green color, the yellow color, probably these are the metal 1 and metal 2 layer lines which have been shown over here, correct? As you go up, the metal layers number actually increases. So this is what I was talking about, metal 1 and the metal 2 line, correct? And now if you go into the some 3D solver, a 3D EM solver, now why do you need to go to 3D EM solver? So if you're designing the circuits around 28 or 77 gigahertz, right, a lot of transmission line effects come into the picture. The model for the inductor that Foundry will provide, you just cannot rely on it, correct? Because there are so many fields that are going on. You have to take care into account the coupling between different parts of the circuit. So what you do is you take your chip, you bring it into the EM solver, and you do the EM simulation to ensure that your chip is working reliably. Now if you look in that EM solver, this is how the chip will actually look like, and it looks very beautiful. It just looks like a city. So I will highly suggest, if some images like this are available, just have a look how chip will actually look like if you try to visualize it in a 3D manner. Right. So coming to the this part, the foundry. So this is our foundry, and what is the output of the foundry? It is nothing but the silicon die. Correct. But foundry doesn't process a single die. It actually process in the batch of the wafers for getting the economies of scale, right? Because foundry has to make money. So the more chips that they are able to make out of a particular silicon wafer, correct, the more amount of money they can make, because the cost for the foundry to fabricate per die, let's say this is the wafer. If I'm able to get 300 dies out of this wafer, and similar other foundry is able to get 400 dies from this particular wafer, right? So the cost per unit die for other foundry is gonna go lower, and the margins of that foundry will increase, right? So they are gonna make a good amount of profit. So now once this wafer is completely ready, so now you have to chop the dice, right? And you do it using the diamond cutter or using a laser cutting technology, and this is how your individual die will look like. Now what you do, the sliced dice that you have, you put them onto the package, and this package then you put it on the PCB. So these are the very different different packages that are available. So if you are doing something on the PCB, you will see most of the high frequency packages, maybe from some different companies for the power amplifier, low noise amplifier. So they will be available in this particular packages. Why not this particular packages? Because you can see there are the lead lengths are so much higher. They are going to introduce so much of parasitics, right? So it does not make sense to use these kind of packages to fabricate at a higher frequency. Higher frequency means I'm talking about 2.4, 8, 10 up to 20, 30 gigahertz, right? So I hope this is very much clear. Now coming to the semiconductor foundries, who are different foundries that are available. So TSMC is the big shot, which contains around 60% of the market share. Then next we have Samsung. Then we have UMC as well as the global foundries, and this is your SMIC from the China. Correct. And if you take a very good view of the package, if you open the top of the package and if you try to look what is present inside, so these were the leads of the package, the legs of the package, which will be sitting on the PCB. And if you look inside, right, so what you are seeing over here, this is what makes the connection between your silicon die and the package. So this is what we call as a wire bonds, correct? So if you want to take any particular node over here and you want to monitor that node outside, you have to assign a pad in the silicon while doing the layout, and now that pad has to be connected to the package, and now that particular leg of the package will be sitting on the PCB, and from that PCB you will be having a PCB, if it is a high frequency signal, then you will be having a transmission line on that PCB, and from that transmission line you will be having some connector, maybe SMA connector, which you can connect with your oscilloscope or your spectrum analyzer and can monitor that particular part, monitor that particular signal actually. Correct. I hope this particular flow is clear. So this is what I was talking about. So this is your package, right? This package, from that particular package you have some passive components that are sitting around this particular package. I have explained the reason for that. And now from that you have a transmission line going on, and then that is connected to a SMA connector. Now this SMA connector you can easily connect with the oscilloscope or spectrum analyzer wherever you want to connect, or you may also want to connect this to a signal generator if this is the input port of your chip. Correct. So this is how the entire structure actually looks like. So from the die, the silicon die, we have actually moved to the package, and from the package level we have moved on to the PCB level. Correct. So now I hope this is clear. So I won't go into very details of it. So I guess this must be clear to you how this how from the silicon we actually fabricate the dies. So you have so you take the silicon, then from the Czochralski process, what you do is you create the ingots of this silicon, right? You basically rotate the mixture and you get the cylindrical shaped ingots, right? And then you slice them, and then you will get the wafers like this. And from on those wafers, the foundry will perform all photolithography, etching, ion implantation, every operation, right? And they will make your circuit. And once this wafer is processed in a batch, then they will slice it and they will send the dies to you, correct? So now coming to the global supply chain of the semiconductor, now who gives the software for circuit designers? The companies like Cadence and Synopsys, right? So they are present in the United States. Using the software from those companies, you design the circuit, you generate the layout. You design the layout, then you generate the GDS file, and that GDS file you send to the foundry. Those foundries are sitting in Taiwan, Korea, Japan, correct? Now, once you have those foundries fabricate your circuit, then these dies that they have fabricated, they needs to be packaged, and those packaging companies again, they may be sitting anywhere in Taiwan, Malaysia, or as well as the Singapore, correct? And once those packages are ready, now those packages will be assembled on the PCB board, and they will be made into the product. And where will that happen? So you know where is the Foxconn, I don't need to tell you, right? The contract manufacturer of the Apple's iPhones, so I don't need to tell you where that functions. And from where does they get the silicon? So it actually depends. So China, so what you can see is over here it is written that it is mined and refined in the United States, but some part of the processing of that silicon actually happens in the Japan as well as the South Korea, because Japan is very much famous for producing very high quality ultra pure silicon wafers, because you don't want any impurities to be present in those silicon wafers. If the impurities are present, then your circuits won't function the way the simulator will give you the results, right? So I hope till this point is clear. And now coming to this particular part, who is supplying the equipment to the foundry? So there is this one company called as ASML, and that supplies the photolithography machine to foundries like TSMC and UMC. So now this is a state of the art extreme ultraviolet lithography machine from ASML. Correct? Can anybody guess what is the cost? What will be the cost of this particular machine? This is a photolithography machine.
Few $1 million maybe.
Yeah, can you tell the number, maybe in crores of rupees or something like that?
Yeah, like 1 million is
$1 million will be something close to 8 to 8.5 crore rupees, I guess.
yeah. So which let's say 10 million, then yeah, whatever, 80 to 85 crores, 100 crores perhaps, 10 to 15 million.
Okay, a little bit close, but still very far away.
Okay,
Yeah, so
20 million maybe, 20 into.
Yeah, so you can
200
see over
million.
here. Yeah, 200 million US dollars. So it costs around crazy thing like 1,500 or 1,600 crore rupees, right? And it is a complete monopoly market. There is no competition for ASML for this particular UV lithography machine, and TSMC will not be able to do any of its job if this machine was not there, correct? So I just wanted you to let you know this thing, because we just see that the foundries are very expensive, they are very expensive to build, very expensive to operate. So this is one of the reason the machines that are going inside, which inside the foundries, so they themselves cost around 1,500 or 1,600 crore rupees, and this is just one machine. Foundry, we may need more machines like this, so just imagine the cost now. So now coming to the companies that are working in the field, correct? So now you have a semiconductor foundry that is present. There are some companies, they design their own products, and they have their own fabs as well. So Samsung and Intel, these two belong to this particular group. And there are some companies who are very good in designing, but they don't have their fabs, correct? They don't want to incur the cost and the headache of running the foundry, correct? So now what they do is they design the products, they send the files to TSMC or UMC, then these foundries will fabricate and send the dies back to those particular companies. Now those dies again, those dies have to be packaged and all, correct? So those dies may be going to companies in Malaysia, Singapore or Taiwan, where they will be getting packaged, and this is how your end products will look like, correct? So and of course there are companies who will be supplying the materials to those foundries, like I just mentioned the ASML, as well as some components are also given by Lam Research Company, a very famous one, correct? So now I don't want to repeat this because I have already done one breakdown. So now what we will do is I have some application case studies with me. Do you want a 5 minute short break to freshen up?
Yeah, sir, we can take a 5 minute break.
Okay, we will take the 5 minutes break now. Okay, break starts now. I guess let's meet back around 7:03 p.m.
Excuse me, sir. I just have one last question
Sure.
before the break. Sir, before you talked about that why short channel devices are not optimal for analog design, right?
Correct.
When you talked about that 7 nanometer FinFET and all of that, you talked about the channel length and all of that. So, I mean, so let's say I'm an analog designer. I want to design a certain chip. If I say that maybe the state of the art, you say that we don't design. You say that we design the chip process using the state of the art 2 nanometer, 3 nanometer, but then the RF chips are not designed using those technologies. So
correct.
Let's say. So let's say I start with 2 nanometer and say, well, this is not optimal, so I just keep increasing the channel length.
Yeah. So you are saying that in the 3 nanometer technology node. So you are saying that I will use the same technology node 3 nanometer, but I will increase my channel length. This is what you are saying?
No. Meaning I'll increase. I'll go up and up in the technology nodes. So it's like, but if I keep increasing it indefinitely, there must be some trade-off, right? So like, how do you optimize like which technology node is best for your?
Yeah, so it actually depends on the application. So if you want to design an amplifier which does not, let's say you don't need a lot of swing out of that amplifier, then you may be able to live with 0.9 volt supply voltage as well. It is absolutely no problem. But if you want a very good gain amplifier which is having a very high speed as well as high swing that will be coming at the output, correct? So then according to swing, you have to first decide where I should go. The supply voltage should not be so low that I will not be able to get any swing out of the amplifier. I will just tell you what I'm telling. Just give me a second. So yeah, so
what's the difference between the technology node and the channel and the W/L, the aspect ratio? What's the difference between that and the
I was not able to hear the second part. You said the W/L ratio and?
No. What's the difference between the aspect ratio and the technology node? Like when you say 2 nanometer, like what exactly does that mean in terms of physically? What does it mean?
Physically, the 2 nanometer channel length physically is just a marketing gimmick. If you actually try to measure the length, right, it won't be 2 nanometer. It is just given a marketing gimmick. If you actually try to measure the length, right, it will be definitely higher than something like 8 nanometer or 9 nanometer. They have been just given the name of that 2 nanometer technology, but I guess this was not your question, right? You're asking something else.
No. I'm saying in the aspect ratio, the W/L, that L is the channel length, right?
That channel length is completely in your control. See, the technology node means that is the minimum channel length that you can have for that particular technology node. So it doesn't mean that, let's say if I use 3 nanometer technology node, I can have devices which can have the channel length of 180 nanometer as well. It just tells you the minimum channel length that the foundry can give you for that particular technology node.
Oh, okay. I get it.
Correct.
Sir,
Yeah.
So my thing was that how do you sort of I mean, look, in analog design in general, it's all about trade-offs, right? I mean,
correct.
In one way, there's a trade-off in some other thing, right?
Correct.
What you try to increase the gain, maybe compromise swing limits or whatever, right? There's all depending on your circuit. So it's like there must be some trade-off between, let's say, going to a higher channel. Let's say I want a long channel device to avoid the, let's say, using the common source amplifier example that you had given, you talked about the output impedance, right? So
correct.
If I keep increasing channel length, then what would be the trade-off there? Like what am I?
So the trade-off will be, see, first of all, why did we reduce the channel length? We reduce the channel length to make the device faster, right? And why we want the faster device? Because if I have a very faster device, then my MOSFET can react very quickly to a signal, incoming signal, which will have a higher frequency. Correct. So now the ultimate trade-off, if you want a direct answer, then the ultimate trade-off, just let me go back to the slide, just give me a second. Yeah, so the ultimate trade-off will be this number, the UGBW number. If you try to increase the channel length a lot, then this number that you are seeing over there, the FT and all, you can see I have not written the formula for FT over here, but FT will actually degrade if you increase the channel length. So now if you keep on increasing the channel length, at one point you will hit a limit where your the desired unity gain bandwidth that you want from the amplifier, your FT number will even drop below that particular number. So now you don't want that to happen actually, because you at least want to keep some margin between the FT and the UGBW. If you ask me, then at least FT by 5 or FT by 6. Correct. So if your FT is around 100 gigahertz, then at least the UGBW that you can easily get will be somewhere close to 15 gigahertz or so, maybe 10 gigahertz. So it will be something like that. So you just cannot keep on increasing the channel length like that.
Okay.
Yeah.
Excuse me, sir.
Yeah.
Sir, can you please explain this Fmax again?
Okay, sure. No problem. Yeah. So this Fmax number, just second. Yeah. Let me have the pen with me. See, if I see, why are we when you talk about the power amplifiers and all, right? So what you are actually doing is, let's say this is your device, right? And now this is your incoming signal, maybe sitting at around 2.4 gigahertz. And now you want an amplified version of this signal. So if I have a signal like this, I want to get a signal which is looking like this. Correct? So the job of the power amplifier is nothing but to suck out the power from the supply, right? And to get that power converted into for this particular frequency. Correct? Or maybe not only a single frequency, maybe that particular signal will have some, if I look at the power spectral density, it may have some modulation around it because it is carrying some information. Correct. So now the job is to take the DC power and basically to convert it into to take that power and use that power to amplify your signal. Now this can only happen if my device has some power gain, right? If my device doesn't have any power gain, you just cannot get this. See, power gain and voltage gain, both of them are different. Okay. So for example, if I take the transformer, let's say 1:n ratio, correct? So you know that if this is V1 and let's say this is I1, correct? I have V2 and I2 over here, correct? You know that for this transformer, V1 into I1 has to be equal to V2 into I2, correct? The power conservation principle. But if you look, V2 is nothing but N times V1. I got a voltage gain from transformer also, correct? But can the transformer give me a power gain? Absolutely no. So now if I plot a power gain, if I take this power gain, and how do we plot it? How do we measure the power gain of the amplifier and all? These are the concepts of the, if you study the subjects of microwave theory and the RF theory, then only you will be able to understand it, because you have to go to into the S parameters to understand this. So if you plot the power gain, right? So there, and let's say this is 0 dB. So now it will start to hit one point over here, and this is what we define as the Fmax. So basically this is the maximum frequency where your MOSFET is capable of giving you any power gain, right? Any power gain. But this number, if you ask me, can we hit this number? If you look in the literature, nobody has designed a circuit exactly at Fmax. They at least operate close to like Fmax by 3 or Fmax by 2, max to max. This is very, very difficult design. If you refer to the latest research papers, you will see people have been designing circuits over here, few people, but the amount of effort that is required, it's absolutely crazy.
So basically, we want a power gain of 1, so it can be only possible at Fmax.
Power gain, we usually want very high number, right? So for example, if I get 30 dB of power gain from this device, that is even better, because I can get a lot of swing from here, correct? But if you say this power gain is just around maybe 5 dB or something, then this is not sufficient for pumping out enough power if I want to send a signal from mobile to base station, correct?
Okay. Thank you, sir.
Yeah, no problem.
I mean,
Yeah,
sir,
just,
like I mean, if we read about all these things under, there's a lot of these buzzwords like millimeter wave systems and all of
Correct.
that. So
Correct. Yeah.
like what exactly is that? I know
Yeah,
it's something related to RF design, but like I want to know
Correct.
exactly maybe like a
Correct. So I have few case studies. Like I have two automotive radar case studies. They have been designed at 77 and 79 gigahertz. I will cover that part over there. Will it be okay?
Yes, sir.
Yeah, sure. Okay, so let's start, I guess. Okay, so now let's move on to the few application case studies, right? Because we want to see where all this stuff is being used in the real world scenario, right? So now let me just turn on the laser pointer. Yeah. So now first case study that I will be talking about is automotive radars. So now when I tell the word radar, I don't want you to imagine a very bulky radars that DRDO may be using, correct? The radars that we are talking about, they have been made for specific consumer electronics application, correct? So now, can somebody's mic is on, I guess. Can you please mute yourself? Okay, thank you. So now this radars, if I tell you the word radar, I want you to imagine a little box which can fit in your palm, or a chip which can fit in or fit on your finger as well, correct? I want you to imagine these radars, not these particular radars, correct? So now if you look why we need the radar, so then you have to go into the autonomous vehicle, correct? The self-driving car. So now radar is nothing but just one of the sensors along with the lidar as well as the camera that you have, correct? So now why we need the radar if we have lidars and the camera? Then the biggest problem is if you are operating in a very dusty and foggy conditions, then your lidar and camera doesn't work at all, correct? You won't be able to get any video because of the fog. The lidars, their performance just drops off according to the light as well as the weather condition, correct? The only thing that can penetrate the fog and can actually tell me whether there is something present in front of my car or not, it is actually radar, correct? So that's why we need the radar, and this is what we call as a concept of sensor fusion. Sensor fusion is nothing but if one of your sensors is not working under any condition, at least have other sensor which can compensate for that, correct? And I hope you may, if you are studying about the self-driving cars, then you may have heard about this sensor fusion concept, right? Now the job is basically to take the images from the camera as well as the data from the lidar and the radar, and then have a neural network which has already been trained, and now let that neural network perceive the environment according to what it has been trained, correct? And now based on that, if it sees that there is suddenly a person who is rushing towards the car, then it should hit the control system and press the brakes of the car, correct? And the car should stop immediately, correct? Now the radar is nothing but just one of the sensors in this particular automotive vehicle, correct? So this is what I was talking about, the lidar and the radar. Even though lidar will give you a very good quality images, good quality images means something like this, correct? These are very bad from your point of view, but from radar's point of view, this is very good actually. So you can see this is a bridge, and there are fin-like structure that are available on the bridge. Those are visible from the lidar. But if you look at the radar, from the radar point of view, you are not able to differentiate between those fins, right? At least you are able to see there are cars, there are two people over here. But if you look the image of this person on the left hand side and the image of the person on the right hand side, I cannot tell whether this is a wooden box or whether this is a metal box or whether this is a person. So this is what I was meaning by the quality of image, correct? And these are just this is just represented in the tabular form. Why we need the radar? You can see all weather operation, camera doesn't work, lidar doesn't work, but only radar is there which can work under all weather operations, right? So now, and where does it fit in your car? So if you take your car, right, if you take near the bumper, right, the bumper area, the black dot that you're seeing over here, so somewhere over here your radar will be fitting over there, correct? And note that there is not only one radar, but actually there can be multiple radars around your car, and the reason for that I will explain very shortly. So now let's move on to the state of the art and let's try to understand few case studies. So the first case study is from the Journal of Solid State Circuits paper, a CMOS 76 to 81 gigahertz, 2 transmitter, 3 receiver FMCW radar transceiver. And don't go into that part, the mixed mode PLL chirp generator, I don't want to go over there, correct? So now if you look, this is what I was talking about. There can be multiple radars that can be there around your car, and the reason for that is you want one radar which can just focus on this particular lane so that it can help you to do adaptive cruise control. What does this mean? So if the speed of this car suddenly drops off, then your car should also reduce the speed immediately. Some radar will be able to help you if other car from one lane is trying to cross onto your lane over here, correct? Some radar which is very short range radar and all, correct? So now it will help you to see whether there are any small objects that are present over here, maybe a dog or cat which has died on the road, or some thing which is coming over here, correct? So that's why you need to create a cocoon like structure around your car so that each and every spot is completely covered by all the radars that are present around your car. Right now, the purpose of this case studies is to just show you where the baseband blocks have been used. We are not gonna go and break down these papers because it will be completely out of the scope of the course, right? So now I don't want you to get feared by looking at this diagram. I was just like you when I first looked at the diagram, and even if you throw me a very recent research paper from a very from a company, or maybe from the same journal of solid state circuits, even I will scratch my head first for 2 or 3 hours, and only then I will get comfortable by looking at the diagram. Okay, so right now just focus on this particular part, right? You can see there is this receiver, there is this transmitter is there, and something is there which is generating a signal that will be given to the transmitter and sent out of the radar, correct? Now I just wanted to focus on this particular part, correct? So this thing is not that easy. You may think that this is just a one amplifier structure, but if you look, this is a complete chain of the filters as well as the amplifiers, and not only amplifiers but the programmable gain amplifiers. Now if you have a very little bit of knowledge about the about this what you can say, the analog circuits, you can easily identify what is this structure. Can anyone please tell me what these two transistors consist of? What do they call as? One PMOS is there on the top, one NMOS is there on the bottom. Does anybody know what is this? This particular block.
Inverter.
Exactly.
Inverter,
Very
yeah.
good. Good. So this is a CMOS inverter, right? And what we have done over here, we have shorted the input and output by putting a resistor over there. So now we are operating this as a in the amplification mode, correct? So now we won't go into the details. Maybe when the course is towards the end, I would like to break one or two case studies. I would like to break down few case studies from the very recent papers if time permits, but not right now because course has just started over here, correct? So now if I move on to the next radar, right? So that was the FMCW radar and this is a PMCW radar. So now what is the difference between the two? So the reason is, as more and more new cars come onto the road, and as there are around 6 or 8 radars in each of the cars, these radars will start interfering with respect to each other. So now instead of if let's say in one particular scenario I receive a signal from somewhere and my radar interpret that as a target, but I came to know that there is nothing present in the environment, it is just the interference from another car's radar, correct? So I want to mitigate that interference. So now I want to put some kind of coding on top of my radar waveform so that I can at least identify my own radar waveform and other radar waveform, which I will treat as an interference, right? So now this is why the PMCW radar has been designed, and so this is the classical paper from IMEC. For all people who are working in the field of analog and RF design or any area in the VLSI, IMEC is a very reputed institution who does very fantastic work, correct? So this is a paper from that particular group. So now again I just want to show you, just to tell you, in the previous case we were actually ramping up the frequency. Ramping up the frequency means, let me just turn on my pen because it will be very difficult to explain orally. So now if I plot a frequency versus time waveform like this, so waveforms that I was transmitting, it was looking actually something like this. So you can treat this as some kind of FM modulation, right? But over here what I am doing is, I have some code over here, maybe a BPSK signal. If you don't know, then just leave it. Maybe when you study digital communication, just come back to the recorded lecture, correct? So now I just have a single carrier, and now I'm having some code with me, and now I'm transmitting that. It will hit the target, the composite signal, it will come back again, correct? And now from the delay, what I'm trying to do at the receiver is to estimate that delay, correct? So this is why you are seeing there are so many parallel chains that are present over here. So you can think of it like I have a time window with me between 0 to tau max, and I am discretizing this, correct? And wherever I will get the peak, that corresponding delay I will mark it as my target, correct? So this is how this radar works. So again, you are able to at least see that the package over here, correct? Then since this frequency is very high, close to 79 gigahertz, if you just calculate the lambda by 2 value, right, you are also able to fabricate the antennas within the package itself. The antenna size becomes so small, correct? And once you have that particular package, you build a PCB board around it, and you can see as all the SMA connectors that I have talked about, the transmission lines and all, everything is present over here, right? And now if you look at the block diagram, again, just don't get fear, right? There are two receiver inputs. Why do you need multiple transmitters and receiver? There is something called as the angular resolution. You want to detect a target. If you want to differentiate between the two targets that are sitting on the same distance from my radar, correct? Let's say this is R and also this is R. So if I want to differentiate between two of them, since the range of the target is same, I cannot differentiate it just by getting the delay, right? I have to move on to some other domain. But you can see that the angles that these targets create around this particular axis, one angle is positive, another angle is negative. So from that I can actually differentiate, and as you will study more advanced courses, especially the antenna, and when you move on to the concept of phased arrays and the beam forming and the antenna array, you will see that you will need multiple antennas if you want to get a good angular resolution, correct? So that's why we have multiple transmitters and receivers, right? Now again, you can see the LNA block, the mixer block that I had told you initially in the example. Everything is present over there, but our main purpose is to just look at the VGA, variable gain amplifier. Now if you look at this particular baseband chain, if you look at the receiver as well as the baseband chain, now you have the LN over here, you have a mixer over here, and now we are just interested in this particular blocks, correct? So our purpose will be, by the end of the course, we should be able to understand what this VGA, how this VGA has been designed, and what this buffer is actually doing, correct? If I want to design a buffer, then if you have done a little bit of analog electronics, you know that if I give an input at the gate of the MOSFET, and if I take the output from the source of the MOSFET, right, this is a high impedance at the input, this is a low impedance at the output, correct? So it acts as a buffer, right? So now there is something, this structure is actually working as an advanced version of this. And how is it working as an advanced version of this? We are using some feedback techniques over here to even lower down the impedance. If you look at the source node, the impedance is 1 by GM. If you don't know this, then it's okay, sir, maybe we'll be covering it. If he doesn't cover, then I will have a quick refresher on this in the upcoming lectures. So 1 by GM is a low value, correct? Now can I use some feedback technique and even make this impedance even lower, so that it acts as a very good voltage source, correct? Very good voltage source means, if this is buffer, and if it is giving me the voltage at the output, if I model it as a Thevenin's equivalent circuit, right, and then there is a load that is present at the output, can anyone please tell me, if I want to have the maximum voltage to drop across the load resistor, what should be the value of RTH?
It should be equal to the resistance.
Just think again. I want the maximum voltage to drop across the RL. So if I write V out, correct? If I write V out,
infinite, the maximum
sorry?
we can have. The maximum whatever we can have.
This is VT.
Zero, sir.
Is this? Yeah, 0, exactly. Somebody said 0,
Ah,
right?
right.
Yeah, correct. So this RTH has to be 0. So what I want is this output impedance should be as low as possible, so that this acts as a very good voltage source, correct? So now at the end of the course, come back to this circuit again and do the analysis and check whether the output impedance has become even smaller than 1 by GM or not, correct? So this circuit is called as the flipped voltage follower, correct? This is called as a flipped voltage follower. So at the end of the course, just come back to this circuit again and just try to scratch your head around this. Okay, now let's move on to the next case study, that is cellular and Wi-Fi transceivers, correct? So now if you look, let's take a very classical ISSC, that is International Solid State Circuits conference paper, and now this is from the MediaTek, correct? And the importance of this paper is so much that the MediaTek's Wi-Fi chip did not came until unless they have published this paper. So basically if you buy a MediaTek's Wi-Fi chip, most probably this kind of architecture will be there inside the chip. Correct. So now again our focus is not to look at all the system side. Our focus is to just look at the baseband side. Correct. Again you can see, if I just want to break down the title for you, 4x4 means nothing but 4 transmitter, 4 receivers. Correct. Why do we have 4 transmitters and receivers in the communication chip? For the radar chip I understood, because I need a good angular resolution. But why do I need so many transmitter and receivers in the communication chip? Now you have to study something called as Shannon's capacity theorem. Correct? Shannon's capacity theorem. If you have studied digital communication, you will already be knowing it. Correct? So now what you can see is that the capacity of the channel, that is the data rate that I can transmit, right? The more the number of transmitter and receivers I have, actually I can transmit at a higher data rate. Correct. So this principle, and how does it happen? There is something called as the MIMO operation. I don't want to go into details of that. Correct. So that is why we need 4 transmitter and 4 receivers, basically to increase the data rate, right? And what does this dual concurrent mean? See, you know Wi-Fi operates at 2 bands, 2.4 gigahertz as well as 5 gigahertz. Correct. So I need a chip which can support both the bands, right? Because if the 5 gigahertz Wi-Fi band is available, why will I not use the 5 gigahertz band? Because there is a good bandwidth available in that band. Correct. So I can download the movie with a very high speed, or maybe I can watch a very good video on the YouTube without any interruption. Correct. Now what does this dual concurrent mean? So there is an advanced concept in Wi-Fi 7. If you follow the this RF industry, so now if you look at the Wi-Fi 7, now if there is some 20 megahertz bandwidth available in 2.4 gigahertz, and let's say there is some 20 megahertz bandwidth available at 5 gigahertz. Now what I can do, I can club the signal from here and here. I can transmit as if I have a bandwidth of 40 megahertz, so that I can transmit with a higher data rate. So basically, if I just write a Shannon's capacity formula, what you can see over here is that the data rate with which you can actually transmit is directly proportional to the bandwidth. So higher the bandwidth you get, higher the capacity. And that is why to get a very good amount of capacity, and since we are moving towards the 5G, already 5G is here, Airtel's 5G you can get at some places, right? If you go to the millimeter wave band, right, around 28 gigahertz, what did I tell you? You can get easily 10 to 15% of fractional bandwidth. So 10% of 28 gigahertz is around 2.8 gigahertz. Correct? Of course, you cannot use entire 2.8 gigahertz because the regulator will just file the case on you, because there are some channel bands that are available. Correct? But at least you can see that if you want to get a higher bandwidth, you have to move at the higher frequency, because you can only get around 10 to 15% of the fractional bandwidth. Correct? So now I hope this concept of this dual concurrent is also clear. Dual means dual band of 2.4 and 5 gigahertz. Concurrent means if there are channels available at 5 gigahertz and 2.4 gigahertz, I can combine them and transmit a high data rate signal. Correct? So now again, if you look at the receiver chain, just don't focus over here, because this is some next level stuff. You have low noise amplifiers over here, then you have the mixers. Now these mixers, also there are 2 types. One is the voltage mode and one is the current mode. So these mixers are actually dumping the current onto the baseband. So now I need a circuit which can take current as an input and can produce voltage as an output. And what is the block that does that? There is a circuit called as a trans impedance amplifier. Correct? And you most probably will be studying this. If not, you must have studied this in the analog circuits course. If not, then just let me know in the next sessions when sir covers circuits like this. Maybe I will try to take an example of the trans impedance amplifier architecture. Correct? So these are all the filters and the programmable gain amplifiers that you are seeing over here. And if you look at the die photograph, so this is complete silicon, right? There is no package. These things, the black things that you are seeing over here. So till that particular boundary, everything inside is a silicon. So this is where your baseband stuff and everything is actually sitting over here. Correct? This is a pretty complex chip. That's why if you go into the paper and if you see, even the area that the chip will be occupying will be extremely huge. Correct? So now again, if you now this is for Wi-Fi side. If you now look at the LTE side, that is on the base station side, I just don't want to scare you, but this is a diagram that I was able to get. Just don't get scared, okay? Now I just want you to focus over here and over here. That's it. Don't focus anywhere else. This is the focus of this particular only the focus of this particular course will be only to study these blocks that are there, that is the baseband amplifiers, filters, active filter, passive filter, and blah blah blah, everything that is included over here. Correct? Again, see over here, again you will be able to see a trans impedance amplifier written over here. Correct? So these mixers, these are actually current mode mixers that have been used. And where will you study this? In the course named RFIC, radio frequency integrated circuits. Correct? So I hope this is clear. Why are we studying this course? Where is it going to be used? See, these are pretty state of the art papers, right? These have been taken just 3 or 4 years back. So I'm not taking papers which are like 10 or 20 years old. So these blocks are still being used. Each and every generation will bring new challenges on these particular amplifiers. So if I just want to tell you one of the challenge, then I had told you about the PMCW radars, right? Now I did not tell you that how does this radar actually achieves a very good, how does this radar actually get very good bandwidth. So now the code that you are sending over here, right? The code that you are sending over here, if I reduce the duration of the pulse, if I just take one pulse, right, like this, and if I take another pulse which has very small pulse width, right, and now if I take the Fourier transforms of both the pulses, in one case I will get a very wide sync lobe, and in another case I will get a very small sync lobe. I am just drawing the main lobe of the sync function. Okay, so now for this particular smaller width pulse, I will get this huge lobe over here. Correct? So it means that it is achieving a higher bandwidth. Correct? So now the bandwidth of the radar, right, it will be decided by the duration of this pulse width that I told you over here. Correct? Now these, if I just tell you the data rate that they have used over here, this is close to around 4 gigasamples per second. Right? This is 4 gigasamples per second. So now just imagine the chip rate that they have, and now once you down convert, I mean you first take this carrier, put it on 17, you take this signal, put it on 79 gigahertz of carrier, right? So after putting it on the carrier, your spectrum will look something like this. This is 79 gigahertz, this may be around 81, and this may be around 77 gigahertz. Correct? So you got the 4 gigahertz of bandwidth that you want. Now at the receiver end, you first down convert the spectrum, right, around the baseband 0 gigahertz, but you are forgetting that this higher end, right, it is still sitting at around 2 gigahertz. Correct? Now what is the challenge? The challenge is to design the baseband circuit which can process such a high frequency signal of 2 gigahertz. Right? If you want to design an amplifier, not only it should give me a gain of 10 or 20 dB, but at the same time its 3 dB bandwidth should be kept high enough to handle the signals having a bandwidth of 2 gigahertz. Correct? Now how do you design the circuit which has a 3 dB bandwidth of maybe around 3 or 4 gigahertz, and at the same time it will give you a gain of around 15 or 20 dB. This is challenging. This is not trivial problem, right? So I just wanted to tell you that new challenges are coming up. They will pop up. Correct? Just do not get feared that your job is gonna get lost because world is moving digital and analog and RF is old stuff, right? So I just wanted to convey that particular message. So now if you just move on to that particular topic, why analog and RF in the world of digital, I will just like to break down into these 3 parts. Do analog and RF jobs still exist in the market? The second is, what is so special about analog and RF compared to digital? And is it worth to put so much effort onto learning all these concepts of analog and RF instead of just taking some Udemy course or Coursera course on maybe some programming or machine learning and AI, and just do that stuff for a few months, not few months, having of course 8, 9 or 10 months, and then get a very high or good amount of package. So now we will try to see this, whether is it worth to put so much of effort into analog and RF or not. So first let's come into the point, do the jobs still exist in analog and RF market? Correct? So now I will just first take some international job. This is from the SpaceX. What I have done is I went to the LinkedIn 2 or 3 days back and just try to search whatever jobs are available related to this particular field. Correct? So now they have posted one job, RF and analog IC design engineer. So now let's see what they are demanding from you. So they want a preferable skill will be to have a PhD in electrical or computer engineering with an emphasis on RF, analog and mixed signal circuit design. I hope till this point it is very much clear what blocks are RF, what blocks are analog, and what blocks are into the mixed signal category. Correct? They also demand you to have a good amount of experience with the simulation tools like Cadence, ADS or the HFSS. HFSS is nothing but the 3D EM solver that I told you about. So that image was actually from the HFSS. Okay, and they also want you to know the knowledge of the modulator, demodulators, the phase lock loop, the mixers, filter, low noise amplifier, power amplifier, whatever we have talked about. Correct? Now once this part is clear and why they want this engineers, so you know what SpaceX is doing, right? So they are sending the satellites and they want to bring the internet from that satellites. So they expect you to also have some knowledge of the digital communication, that is the constellation diagrams that I had shown you initially, right? The QPSK, QAM and all. So they want you to at least have a basic knowledge of the digital communication. Now coming to the Indian job, this is the job that was posted by the Silicon Labs. Again, you can see they are not mentioning the very state of that technology node like 7 nanometer FinFET and all. They are mentioning 113 nanometer technology node, which is old back, right? Still circuits are being designed, still products are being released in this particular technology node, right? They want you to have experience around this particular technology nodes and designing the circuits that I just told you about. They want you to have understanding about the passive devices as well as the EM simulations on this type of passive structures, right? And again, they are demanding the experience in the Cadence as well as the EM simulators like ADS as well as the HFSS. Now coming to RF and millimeter wave jobs. So this was the job that was posted, I guess, few months back, if I'm not wrong, from the global foundries. Again, they demand you the experience of having design experience in all those blocks, the LNA, PA, VCO, phase lock loop, modulators and everything. And now coming to the power management job from the Texas Instrument. Again, they want you to have a good understanding about the operational amplifiers, the band gap preference circuits and the regulators that I had shown you about in the power management slide, where I had shown you about 25 to 30 different supplies that are required in your mobile and you have to generate them from single lithium ion battery. Correct? So after look, and one more thing that I just wanted to tell you, right now a lot of SerDes jobs are booming. So SerDes jobs are nothing but the wireline communication, the communication that happens between the processor and the memory, right? Which is at the speed of 20 or 40 gigabits per second. A lot of those jobs are actually booming up right now. Can anyone please explain why there is so much of need for SerDes jobs, that is the wireline communication guys, and why these jobs are actually coming up in high numbers right now? It is just the communication between the two chips, that's it, the processor and the memory. Can anyone guess?
Hello.
Hello, yeah.
I think the processors have become faster and faster with each passing day.
Correct,
So
correct, but correct.
we have
You are
we have
absolutely on the right track. No, but
yeah.
why
So
there is so
we
much of boom about the GPUs and CPUs right now? Who has come into the picture?
NVIDIA is in GPU as what I know.
Sorry.
So NVIDIA is in GPU
Correct, correct.
domain, right? Yeah.
Correct, correct. Yeah. So why there is so much of demand for their products, and where do these products actually go? Do you know that?
It is hardware acceleration for AI. The requirement is for
Exactly.
hardware
Exactly.
acceleration
Very
in
good.
AI.
Very good.
The
So
higher
with
data,
the
yeah,
correct, correct. Go ahead. Go ahead.
the higher data rates that the accelerators usually require, like communication between various FPGA blocks and all. So that
Correct, correct.
requires these things.
Yep. Good, good. So let me just go back to the slide. I had that slide with me. Just a minute. Yeah, so inside these data centers, just like this guy said, so inside these data centers, if you look, there are multiple racks, and this is where the need for this having a high speed interface between the CPU and the memory actually comes into the picture. And if you want to go into the details why this has become such a huge problem, right? So now just search about the memory wall bottleneck on the Google, or just search on the chat GPT itself. Just understand what is memory wall bottleneck and just see how much power is actually burned while transferring the data between the memory and the CPU. So now how can I transfer a very high speed data between the CPU and the memory by consuming as low power as possible? Correct. So now this is where these jobs are coming into the picture, and that's why if you talk about our research group, even though we work on the radars and the RF field, many of my seniors are now working on the SERDAS area only. Correct, because there is so much of demand. And why did this demand came? Just do not forget that the market is still driven by the digital guys, and those digital guys, because of their needs, we have got this job, what you can say, regarding the SERDAS. So they want you to understand how this SERDAS circuits, the wireline communication happens actually, and how to design the circuits for this particular application, right? So I have this, that part is clear. And from where will the future jobs will come into the picture? So you know that the spectrum around this 900 megahertz 2.4 gigahertz, it is extremely crowded. And I have shown you from the Shannon's capacity theorem formula that if you want to get a higher data rate, you need to get a good bandwidth, and you cannot get a good bandwidth where the spectrum has already been congested. You can get a good bandwidth only when you move up to a higher frequency where nobody is using the spectrum, or relatively a wide amount of spectrum is available. Correct. Now how can you go to the 100 200 gigahertz frequencies and still make your circuits work around that particular frequency, right? Now the challenge is how to design RF front end, that is low noise amplifier, power amplifier around 100 200 gigahertz. And once you solve that challenge, there is one more challenge. Now the data rate that has been targeted around this particular bands, it is absolutely crazy. It can even go to I'm talking about the wireless links. So now that data rate can even go up to even like 30 40 or even 50 gigabits per second. Now once you have the once you solve the RF front end problem, now how will you design the baseband circuits which can handle such a high data, 30 gigabits per second? That means your 3 dB bandwidth of your amplifier has to be higher than that, or else it will create the distortion. Because distortion is created when the different frequency components are amplified by the different gain by the amplifier. You want all the frequency components to fall to get amplified with the same gain, right? Now how will you design the amplifier which will have such a high 3 dB frequency? So to design that, you need a very high unity gain bandwidth amplifier, and those designs are not trivial. I'm not saying work has not been done. Work has been done over there, but nobody, if you look at circuits which are designed at 200 300 gigahertz, and if you talk about the power consumption that is there for baseband circuit design as well as the analog to digital converters, nobody actually talks about it. The power consumption of the analog to digital converter itself can go up to 5 or 6 watts. 5 or 6 watts of power just your ADC is consuming just to sample 20 or 30 gigabits per second signal very reliably. Correct. So how will you solve the challenge? How can you bring down the power of that ADC low enough so that we can still work with it and still the signal is at the reliable level? Correct. So these are some of the areas where the future jobs can come into the picture. Now this was for the communication side. From the radar side, again I want a very good bandwidth, because good bandwidth gives me a higher resolution. Resolution means you can think about the image resolution kind of thing. I don't want you to go deep into the radar. Just think of like the images that I have shown you for the lidar and radar, and just think that the resolution of those images will get better if I transmit a signal from the radar which has a very wide bandwidth. Correct. Again I have to move on to the higher frequency range over here. Correct. There is one more area coming up called as a joint radar communication. So now again that area moves around this particular frequency, where the challenge is to design a hardware which can not only transmit the communication but it can also transmit the radar waveform. So how can you optimize your hardware, the RF front end and the baseband, so that it can not only transmit the radar as well as the communication waveforms? Correct. So these are some of the areas where research is happening, and the future jobs will most likely come from those particular areas. This is where the technology is moving right now. And what is so special about the RF and analog? So now the first thing that everybody asks me, will AI and chat GPT eat into my job? See, I will tell you, the automation has already started to happen in the analog for very basic blocks. Like the two-stage op-amp, the topologies which are very, very familiar and which are very mature, correct? So they can just give you the width and the length of the MOSFETs. They can just give you the biasing conditions, and you just get that circuit in the cadence. It will most probably work, correct? The automation has also started to happen in the layout, but the problem occurs when you go to the RF side, correct? I just told you, if you move to the higher frequency, you have to shift a lot between the your cadence software where you are designing the MOSFET transistor level circuits, and you also have to go into the EM simulations. Now from that EM simulation results that you will get, you again have to tune something in your circuit, correct? And again go back over there. So now the problem is, how will you automate this? Like, because you are not using a single tool, you are now switching between 2 or 3 different tools over there, correct? And so a lot of these things come from the experience, which is extremely hard to automate. Now the digital has been automated up to such an extent that even if you don't understand transistor very, I mean, of course I'm not saying don't just ignore that part, but if you just write the Verilog code, right, the tools are there which can easily generate the layout for you, correct? That kind of automation has not yet happened for the analog and RF. And even if that automation happens, right, slowly and slowly, the jobs are not just gonna get vanished. The jobs will become even more advanced and even more tough. The only question is whether can you handle those tough jobs, whether do you have that fundamentals with you to handle those tough jobs, or whether your knowledge is just a commodity which can which everyone knows in the field, correct? So that is the question that you should just ask yourself now. And one more thing is, just look at the second point. You know that you get the headlines about IITMs getting 1 crores, 1.5 to 3 crore rupees of packages and all, right? So now the thing, if you look at those companies, the investment banks, the finance and the consulting companies, they require a very sharp aptitude from a person, right? They require an extremely sharp aptitude, extremely smart level person. But the jobs that I showed you on the LinkedIn, right, they demanded you a more experience, a more knowledge of the circuit. So the more time you spend on designing the circuits, understanding them, have a pen paper design, and more time you spend on the tools, you are gonna become more valuable in the market, and there is a good chance that you will be landing into a good job. Now the last question, is it worth putting the effort, correct? The where the effort, I mean, whether I will be getting good package to so that I can live a comfortable life or no. So this is a question that we should ask. And now I will be revealing some data. I just request you to please not share it, or please not take the screenshots, and at least don't tag me over there, correct? Because this is the placement data that I have taken from the IISc, correct? So now if you look at the 2022 batch, so now if you look at few companies like Texas Instrument, Qualcomm and Samsung, everybody offered a good CTC, 37.45 lakhs per annum, and the base, if you ask me, it was close to around 22 lakhs per annum, right? Now again, if you go into Intel, the salary was little bit low, but if you ask me, the base was very close to around 18 or 20 lakhs per annum. TSMC definitely comes every year and at least hires 1 or 2 people from IISc, and they give a very good package, one of the best salaries that you can get in Taiwan, right? Now the problem is, now the thing is, whether it is worth to put so much of effort to crack the gate and then try to enter into the institutes and then do the MTech and then get these packages. It is completely up to you what you want to do. If you want to go abroad for the masters, I will highly recommend it if you are getting good universities. But the only thing is, I can say that the semiconductor industry in India is just on the cusp of the growth. Whatever knowledge you earn in the foreign, I want you to go there, study, earn a hell lot of money, but I just want you to come back and start your own company or do something over here, so that our country also benefits from that, correct? So we are just on the cusp of that particular growth, right? So any questions till this particular point? If not, then I will just solve few numericals that will help you to solve assignments, and after that we will just close the session. Any doubts till this particular slide? Okay, I guess we will solve few numericals now. Just let me turn on the pen. So now, yeah, so this part, the negative feedback and all, I will just cover in the next slide, because I just want to cover few type of numericals that will help you to solve the assignments, because that is the main purpose of these sessions, right? So now just give me some time. Yeah, so now let's start solving few numericals. Let's start from a very easy numerical, right? And by the way, if you want to refer to the sources, I have below the images I have mentioned the sources, so you can go back to those documents and refer the what they have given in the document. Correct. So now let's try to solve this particular question over here. Correct. So now what is this block over here? So now if I by the way, all the op-amps will be ideal in all the questions that I will be solving right now. Correct. Ideal op-amp means you can apply virtual ground. Virtual ground, you can assume that there is an infinite gain that is present in the amplifier. Correct. There are no offset voltages, nothing is there. Correct. So now how to solve this question? So they have given us this voltage source. There it looks like some kind of a resistor divider. Then there is a voltage follower circuit that is present. Why voltage follower? Because I can easily this is a negative feedback, right? And I can have these voltages to be equal because I am applying virtual ground. Now if I have this voltages equal, again there is looking like some kind of voltage divider. Now just one question to you guys: what will be the current going into this node? Can you please tell me?
Zero? Should ideally be zero.
Zero. Good. Because input terminals will have infinite impedance for ideal op-amp. Correct? So now if this terminal is open, right, this block just became like a resistor divider for me. Correct? So now I will first find out the value of V1 over here. Correct? So now V1 will be nothing but 7.5 into 24 upon 24 plus 16. Correct? So now this will be just I guess 6 by 10 into 7.5. So now this V1 value will be I guess 9 by 2 equal to 4.5 volts. So we got the value of V1. Now this value, whatever value I have over here, I can put it over here also because of the virtual ground principle. Right? So now this V2 became 4.5 volts. Correct? This became 4.5 volts now. And now this 4.5 volts over here, right? Again it is a resistor divider, nothing is there. Correct? So now the circuit, the voltage, if I want to calculate VO, so VO will be nothing but 12 upon 12 plus 8 into V2. This is V2, right? V2. And V2 is what? V2 equal to V1 equal to 4.5. So now if I try to calculate V0, right? So now this will be 12 by 20 into 4.5, or maybe I can write it like 3 by 5 into 4.5. So the value of V0, if you calculate, the value will be coming close to around 2.7 volts. Correct? So they just wanted us to calculate the value of this V0, this value of V2 as well as V1. This was a very easy question, but that's the way you do it, right? You start with the easy and just increase the difficulty slowly. Correct? So now let's look at this particular question. Now they are asking us to calculate the I0 in milliampere. Again, the op-amp is ideal. Now the problem with this question is, you can see there are two feedbacks. One is around the negative terminal, one is around the positive terminal. Right? Now how to solve the questions which have two feedbacks in them? Correct? The only way I can see, I need to apply the virtual ground, right? My life will become very easy if the op-amp is negative or it is operating in the negative feedback. Now there is only one way. I just need to check the strength of the negative and the positive feedback. Correct? Whichever is stronger, then I can at least tell whether I can apply the virtual ground or not. Correct? So now to check the strength, since what we have to do is, I will apply some disturbance on the V0 and I will try to check what is the signal that I will be getting at VN and VP nodes of the op-amp. Correct? This is what I'm gonna do. So now if I'm already applying some input over there, I need to short all the voltage sources that are present in the circuit. So now what I will be doing, I will be just shorting this for that particular purpose. Now if I give an input at V0, right? Now this is again at the input. See, I just wanted to check for the strength of the negative and positive feedback. But since the op-amp is ideal, again the current that will be flowing into the negative and the positive terminals, they are going to be zero. Correct? So this voltage I can just find out, it is nothing but a resistive division between 10K and 1K. Correct? So now if I calculate the VN voltage, correct? So from the output it is looking as if the voltage across the 1 kilo ohm resistor over here. Correct? So 1K upon 1K plus 10K into V0. Correct? How much it came? 1 by 11 into V0. Correct? This is 1. Now similarly I need to find the VP also, correct? Now since I have to short other voltage source over here, this 1k resistance and this 1k resistance will come into the parallel, right? And if this come into the parallel, then the effective resistance from this particular node, correct, will be just left as 0.5k. I hope everybody sees this, correct? I'm just combining this and this into one shot and just writing it as a one resistor over here, correct? Now if I do this again, I see from the output it is nothing but a resistive division between 12 kilo ohms and 0.5 kilo ohms, correct? So now VP, if I try to write 0.5k upon 12k plus 0.5k, correct? So the VP value will come out to be around V0 upon 25, right? Now can anyone please tell me, by looking at these two values, what do you think, negative feedback is stronger or positive feedback is stronger?
Negative.
Negative, right? So I can definitely apply the virtual ground principles, and what we have to do is we just have to apply one KCL at one particular node and then we are good to go, correct? So now I will just rough these drawings over here, just a minute.
Excuse me.
Yeah.
Is there a rule of thumb as to how much stronger the negative factor has to be than the positive factor to apply virtual ground?
Okay, so even if, see, we just want to check which feedback is actually dominating. So even if the negative feedback is a slight stronger than the positive feedback, that is still okay. The problem actually arises when the negative and the positive feedback, they exactly become equal with respect to each other. So even if it is very small, very slightly larger than the positive feedback, you can still do the job. You can still apply the virtual ground.
All right, got it. Thank you.
Yeah, correct. So let me just rough this. Just give me a minute. Yeah, I'm just rubbing this because we have to apply a KCL over here. It will just become a complete mess if I don't rough it, right? So now what we have to do, we just have to find the value of this I0. So to find the value of this I0, I want to know this voltage over here, correct? Now how to know the voltage at this particular node? What we have to do is we have to apply a KCL at this particular node to find out the value over here, correct? This voltage is given as 1 volt, correct? Now I will write this as Vx, and now I will apply KCL at Vx, correct? So now for this particular path, the KCL will be Vx minus 1 upon 1k. Then for this particular path, the KCL will be what? Vx upon 1k. Then for this particular path, the KCL will be what? Vx minus Vo upon 12k. Now this has to be equal to 0, correct? And now if I see, this is Vx is there and this is V0 is there, correct? Now two variables are there. I want to make sure that this equation reduces to a variable of only this equation reduces into only one variable, not two variables, correct? Now just now we have seen that since the negative feedback is stronger than the positive one, I can apply a virtual short principle. Again, if you look, there is no current flowing over here. This voltage we have already calculated, right? It is V0 by 11 at this particular node. And again, if I transfer it over here, I can see that, let me just write this as equation number A. I can see that V0 by 11 will be equal to Vx, correct? So now what I can do, I can just put V0 is equal to 11 Vx. Let me highlight as equation number B. Now what I will do, I will substitute the equation number B in equation number A and just try to find out the value of Vx from equation number A now, correct? So now I will just write over here from A and B, right? If you now try to substitute this, what will you get? So first I had this Vx minus 1 term, correct? Then I had this Vx term, and then I have this Vx minus V0 upon 12k term, correct? Right now we just said that we need to put V0 is equal to 11 Vx, correct? Now if you put over here, what will you be left with, correct? You will be left with like minus 10 upon 12 into Vx. Now this correct? So now this will be equal to 0. Now what you have is 2 minus 10 by 12, correct? From here and from here, Vx is equal to 1, correct? So what did you get? So if you just solve this, the value of Vx will be coming out around 12 by 14 or equal to 6 by 7 volts, This is the value of Vx that you will be getting. Now, what was the question? Question was not to find Vx, question was to find the value of I naught. I naught is nothing but Vx divided by 1k, right? I naught is nothing but Vx divided by 1k. So now Vx is 6 by 7. So this will become like 6 by 7k, right? So now the answer for the I naught is nothing but your 6 by 7 milliamperes. I hope till this point it is very much clear. I guess we are up in the time. The rest of the examples, they will at least take some time and we will be overshooting. So I guess I will be stopping over here. If you guys have any doubts, then please feel free to poke me. This is a good time to ask questions now.
Hi,
Yeah.
Murali. My name is Murali here.
Yeah.
I had a question. So, how do you differentiate between the power delivered by the voltage source and the power delivered by the op amp here?
Power delivered. Just give me a second. Yeah. Or tell me again.
So, in assignment 1 for this course, right? There was a question in which they asked the power delivered by the voltage source and the power delivered by the op amp.
Okay, so since it's an assignment question, I just cannot directly solve it. I will just give you a
How
hint.
do you? Yeah, exactly.
Yeah.
Yeah.
So
That's
now
what.
the power. See, if I just have a voltage source over here,
Hmm?
correct? So how to check what is the power delivered? So if I just calculate the current that the voltage source is actually the current that is coming out of the voltage source, and if I just do P is equal to VI, this will give me the value. This will give you the value that the power that will be delivered by the voltage
Current
source.
voltage source. That correct? Yeah.
Correct. Right.
Hmm.
Yeah.
And what about the power delivered by the op amp? How do I find that then?
Power delivered by the op amp.
Yeah.
Okay. Yeah. So that's a tricky question. Yeah. Just give me a second. Let me just think about it.
Oh.
We can use power conservation law. Total power dissipated and total power given from source.
We can
Yeah.
apply KCL at the output node.
Yeah. You can.
And
You can.
then,
I guess. Yeah. Both the answers are correct. That both the guys said.
then we can find output current of op amp.
Correct, exactly. So you need to find the current over here and then you need to find that output voltage. Another one way, a little bit longer, is to check how much power is actually delivered by the source, then calculate whatever power has been dissipated in each and every component and just apply the power conservation principle. That's it.
So essentially, you're saying that the power dissipated will be equal to the power delivered by the op amp, is it?
Power yeah, so the net power consumption, it has to be conserved. So it cannot happen that so the power delivered has to be equal to power dissipated. That's it. Just apply this principle. Because
So,
if
okay,
this does not
a
get
follow-up
balanced, so
question there then.
sorry.
So, a follow-up question for that then. So, for example, if you consider the 1K that is connected at the positive terminal, let's assume that there's something, the voltage that is connected. We get a voltage there due to the input 1 volts, right? So, because of that 1 volt, there is a current flowing there through RL and the other 1 kilo ohm. So, now because of that, there is some power dissipated on that because of the input source also, that voltage source also, right?
Yeah, correct. See, if you think about the op amp, there is also a power source that will be connected. VDD is there, minus VDD is also there, right? So for power to get dissipated, you need what you can say. You need that power. If you just remove the source from here, if you just remove the source, then who is actually supplying the power to the network?
Okay.
Yeah, so somebody has to be there to supply the power.
Okay.
Yep, correct.
Okay.
Yep, correct. Any doubts? Any more doubts?
Just a question, like in case this virtual ground concept would not have been applicable over here, then what approach we could have taken? Because in that case, again, the current through the op amp, also like some current would have flown through it, so it would have been very complicated, right?
Yeah, so just think about it. The op amp has a almost infinite gain, correct? Because it's an ideal op amp. And now that too, you're operating in the positive feedback now. correct? So now what happens in that particular case? So normally where we use the circuits having a positive feedback, either in the Schmidt trigger or either to construct the oscillators, right? So now the way it will happen is output voltage will actually grow and it will just what you can say, it will just saturate to the supply voltage, either the positive or negative, or if there is some kind of hysteresis that is going on in the circuit like the Schmidt trigger, then you have upper and the lower voltages that have already been defined where the output can actually reach. So that is how I will answer the question.
Okay.
Yep, correct. By the way, was the lecture boring? Like, did you get bored because I consumed a lot of time at the start, or?
It was awesome, sir.
Awesome, great. Good. Yeah, so I guess we are good to go. I guess we are already 2 minutes over the time. So if there are no doubts, I guess we can just close this session, right?
By any chance, will we be able to access the recording of this lecture if possible?
Okay. Thanks a lot for reminding me. I will just post the YouTube channel link. Just a minute. Yeah, great. Yeah, just say I have posted a YouTube channel link, and in the description section you will be able to find the lecture notes as well. And I also posted some extra questions which I was not able to take. So what I will do, I will just solve them and put it on the PPT so that you can at least refer it while solving the assignment questions. I hope that's okay.
Okay, thank you so much.
Yeah, great. Take care, guys. Happy Republic Day and have a great weekend ahead. Take care. Bye bye.